Merhaba, welcome everyone. Thanks for joining us today for our webinars regarding simulations in the plastics industry. It's 2 o'clock in Turkey, it's 1 o'clock in Germany. I suggest we wait for another 1 or 2 minutes because people are joining. So just give us 1 or 2 minutes, please, until we start. Okay, we can see more people are joining. That's great. Happy to have you here. Okay, Merhaba, welcome everyone again. I think now it's time to start our webinar. We are happy that you are here with us today. My name is Hendrik Evers. I work for Janus Simulation. But before we start into the simulation part, we have a guest here, Can also. Please introduce yourself. Why are you here today?
Hi everyone, I'm Can also. Actually, I specialized in CFD side of engineering, but I'm working as a CAE application executive in BİAS. Because of that, I attended this webinar. We are new representative of Janus Simulation in Turkey, and happy webinars to all.
Great. So, Can, if you want, you can start with your short presentation. Then, yeah, I will proceed, and after that we go into the live demo.
Yeah, thank you very much, Hendrik. I briefly explain BİAS engineering today, who we are, what can we do for our customers, and it takes 3 minutes as well. Firstly, BİAS has founded in 1997 and providing advanced engineering solutions to the organizations such as defense, aviation, aerospace, automotive, and railway systems. Initially established for CAE, the company expanded its field by engaging in test and measurement design and R&D activities and founded spin-offs in these areas. We are calculated in 4 cities in Turkey, which is Istanbul, Ankara, İzmir, and Bursa. By the way, our engineers take 70% of the total employees number. With the number of 30, the largest department in BİAS is CAE team, which reaches to 25% of total engineer amount as well. We have test facilities in Istanbul and Ankara, which is one of the biggest private test facilities in Turkey. From strength and life tests to conditioning cabinets and from shakers to engine tests, our facilities enable testing a wide range of engineering problems as well. We are representing several test, measurement, and CAE companies which are the best in their field, and one of them is Janus Simulation. As you can see in the presentation, our softwares are the most powerful one in FEA, CFD, MBD, and acoustic, which are Nastran, Cradle, Adams, Actran, Romax, and Janus as well. We also have co-simulation capabilities with different disciplines such as fluid structure, interaction, and aeroacoustics. We have the capability to manage all software-related processes, including training, technical support, engineering services, pre-sales and post-sales activities. We can also provide engineering services, and you can see our expertise in engineering services for different disciplines, from the NVH analysis to the multi-body dynamics analysis from our From analysis of composite structures to aerodynamic analysis of aircrafts, we have a large team of experts in their respective fields. Thank you very much. You can type us from destek@bias.tr and happy nice webinar again.
Thank you, Can. We are great and happy that we have you here today. And also we are happy to have you as our partner in Turkey. So regarding simulations, I will share my screen. I only have 2 PowerPoint slides. Those are the last 2 PowerPoint slides you will see today before we start into the live demo where you see how our software works and how it could help you in your daily business when you design new tools. So the first question I brought with us today is, why should you simulate? What's the reason? Why should you do it? I mean, you are experts in your fields. Maybe you work with experience for many years, but why should you now switch and start implementing simulations? The most or best reason for it is that you are able to make informed design decisions. In the past, without simulation, you built the design, you built the prototype, you tested it, you experienced some problems in the prototype. Maybe the velocity or the viscosity is not right of the extrusion, for example. Then you have to do rework loops, build a new prototype, test it again, and you face another type of problems. So you have to do all these loops, rework, design, test it, rework, design, test it. And that costs a lot of money and a lot of time before you are able to launch your product. With simulation, you switch to digital twin testing. So instead of testing your physical tools, you develop your physical prototypes, you test on digital twins, which is much faster and much cheaper. Why is that? Because first you create the design, you simulate, make a little adjustment on the design, build the prototype, test again, and you have less rework loops. Because in simulations, you see directly where something is not correct with your tool design, where you should do improvement. And that means you have a higher profit because you have a lower development time, you have less material waste, and you are able to produce more tools. So you are able to sell more. You have a better customer satisfaction because the faster product delivery and less rework necessary create a more happy customer. And of course, you have a less headache because you don't have these customer complaints like maybe you used to. And also the development process is much smoother. If you choose to simulate, which is the modern way of creating new tools, why should you use Janus simulation software? First of all, we are cloud and web-based. That means you don't need any expensive hardware. You don't need to install anything. You don't need to update anything. We do that for you. We are cloud-based. You simply log in like you used to log in into Instagram, Facebook, or LinkedIn. Our software, and you will see that in the live demo in a minute, is very intuitive and easy to use. So you don't need to be a simulation expert. It doesn't matter if you have simulated already or not. It's very easy to use. You don't need the knowledge. There's no complicated user interface. You can literally start right from the spot. Why is it so easy to use? Because we use fully automated workflows. That means everything is automated. You can start a simulation within 5 minutes. You don't need any extensive trainings. And because we calculate in the cloud on high performance clusters in Germany, we receive very fast and reliable results because those high performance clusters are among the fastest in Europe. And now maybe some of you are already using simulation software and say, hey, I'm using this, I'm using that. That's totally fine. Don't switch from it. You can use us in addition to your current solution. You can take pressure from your simulation department. You can enable your salespeople who are maybe not so familiar with the technical simulation thing to simulate and create better offers. Or you can also do faster experiments when you use parallel simulations. That's the final part of this presentation. Now I think it's time to head into the live demo with my colleague Simon Link.
Yeah, thank you, Hendrik, and yeah, hello everyone, and welcome from my side. My name is Sam Link, and I work at Janus as application engineer. And yeah, today I will go into the technical details, give you an overview of the simulation for the plastic injection molding and the plastic profile extrusion. So maybe again, yeah, very shortly, why do we use simulation? So Hendrik already gave an overview of the benefits of the simulation. And yes, we use them to make better decisions. So what does this mean? So for example, we can use simulation to create more accurate quotations by providing reliable estimates of cycle times, and yeah, thereby also evaluate the manufacturability of the parts before it goes into the production. And we can also use it to predict and optimize the manufacturing process. So this is something we see on the real applications with our customers, that we can reduce the development time and also the cost of tools. And yes, we can also reduce the amount of material needed for the testing. So yes, I will share my screen now. And give me a second.
By the way, while Simon is going to start sharing his screen, if you have any questions regarding the live demo, regarding BIAS or Janus simulation, please feel free, just enter the question into the chat and we will be happy to answer the questions at the end.
Okay, perfect. Thank you, Hendrik. So yeah, today I have the pleasure to show you how easy it is to start the simulation in less than 5 minutes here with our simulation tool. And yeah, what you can see is our cloud-based simulation platform, which we call the Strömungsraum. And you can access it with your web browser at simod.de. You can see it here on the top left corner. And you can access it basically from everywhere. You just need to have access to the internet. And you don't need a specific hardware. You can use it with your normal computer. You can use it on your laptop. You can use it on your tablet, because all the computation and all the hardware is located in the cloud on our side, and we do the computation for you. So no specific hardware is here required. And you can basically go everywhere online at simod.de, and there go start a simulation and also look at the results. So I will give you an introduction here on how easy to start a simulation. So let's start first with the profile extrusion. And what is basically important, that we upload a new 3D model first. And when we have the extrusion die, we can create the flow channel of the extrusion die. So this is very important. So this is the fluid domain where the melt is flowing through the die. And we can basically consider every flow channel at the beginning and the end of the extruder to the end of the extrusion die. And here you can see a few examples. For example, for the flow channels for this PVC multilayer profile, as you can see here. So we have 2 profiles extruded in this case. We have this spiral distribution. You can see here we have this multilayer profile, where we'll have a closer look to in the next minutes. And we also have the slit die here. You can see we have this cable coating we can do the simulation for, and we also this single layer profiles. So when we've created the float channel from the extrusion die, we go just here to a new 3D model. We go to the file browser. We can then select the file, and we support different formats like exchange format like STEP, or native formats, as you can see here, like SolidWorks, Inventor, NX, and Parasolid. And you simply enter a name, click create, and then the model is being uploaded. So then we go to this float channel. We say, okay, we want to start a new simulation here. And what happens next is that we have to decide what we want to do. And we want to do the extrusion die simulation. And we have to enter the inflow temperature first, like, let's say 120 degrees Celsius. We select the material base, and we have a very huge material database, and I will select this ABS here for now. And inside there's also the processing temperature in this case for we can change that if we want to run at 80 degrees also. Then we have to define the throughput, like 150 kilograms per hour. And the model I selected is a co-extrusion with two different materials. So we need to define the second inflow, as you can see here. We select, for this example, a different material. We define the throughput here also, and then we confirm this with next. And what you can see here is summary of all, an overview of all the configuration we've made here. So we see the inflow temperature, the material information, and so on. And when everything is correct, we can start the simulation here on the bottom of the top right. And what's basically happening next is that the simulation is then submitted to one of the HPC clusters, so the high performance computing clusters, where we have computational capacities. And then everything is done completely automatically. So we start with the pre-processing. So this means the geometry preparation, the meshing itself, the simulation, so the solving of the simulation, and also the post-processing, where we also generate the simulation report completely automatically. So how long does this take? It's usually depending on the model size, and if we have very small features, we have a finer mesh, then this will also increase the simulation time. So it's usually between 30 minutes and a few hours. For the profile extrusion and the injection molding, what we always say is that if we start a simulation at the end of the day, then we will have the results overnight. So if we're back in the office at the next day, then the results are finished and we can have a look at them. And as soon as the results are there, we get a notification by email, and then we can have a look at them. And I will jump right straight here into the report. So this is the report that is generated completely automatically, and we can customize it up to your needs. So if you say, we got here some kind of plot that you don't need, then we can remove it, and we can also add new views and also new plots if necessary. So let me give you a very quick overview about what's inside here in this simulation report. So we get information about the process data. So the information about the different inflows, the material that has been used, the temperature of the melt and the tool, and the information about the throughput here, and also what's simulated then. So what is the average velocity looking like, which is very important at the exit of the die, and also the variance. So we basically want to aim for more or less uniform velocity distribution at the exit of the die. So the variance should be as small as possible. And we'll give you a very quick overview about of the different measurements we have. So like the pressure plot. So here we can see the different pressures inside the die. So of the melt itself, and we can then detect areas which have a higher or smaller pressure. So we can see what's going on here in the extrusion die. We get more insights, and we can then make improvements to our die. So basically the most important plot is the one here for the velocities, as you can see here at the exit of the die. And the scale here shows the velocity. So blue is almost velocity of 0 meters per minute, and red is a velocity of around about 7 meters per minute. And what we see is that we have here very low velocities or small velocities in the middle of the profile, and on the outside here we're having much higher velocities, and on the top here there are also very small velocities. So we also see this velocity hotspots, what I call them, and this can be a problem, of course, in the manufacturing process if we don't have this more or less uniform velocity. So we can then go back into our tool design and make adaptations. So we can detect areas, and maybe in the middle we can decrease the resistance of the flow, and on the outside so we can also make adaptations to reach a more uniform material velocity. So we also have many other measurements. I will go through it very quickly. So as you can see here, we also have these plots with the different cross sections and slices. And here you can also go very into the detail and have a look what's happening really inside each of these cross sections. We also have this for the viscosities, so you can also look at the viscosities and detect dead zones here, for example, in areas with very high viscosities. And we have this same view for the viscosity also, and also for the shear weight. What's very important also the plot here of the streamline, so we can see which paths the melt will take, beginning from the two different inflows, and then we can also calculate the residence time. So we can by this detect areas which maybe lead to a very high residence times for the melt when it's moving through, and then we can aim for changes, improvements for this in the tool design. What's also very interesting is here the material distribution, as you can see here. So this is a co-extrusion profile. We have two different materials. In the inside, we have the blue old material, and on the outside, there's this new virgin material in green. And we can detect the layer thickness, as you can see here. We can see, do we have a continuous layer or not? As you can see here on the top, so there's the profile is not covered by the green material at all, and we can also see that the material here is moving the green one into the profile, and this makes it more easy for us to do improvements to the tool even before the manufacturing. So if we want to get even more insights, we also have this live viewer, as you can see here, and we can then have a more detailed look in it. So if I switch here to the velocities, this can take a second to load. Yes, now it's loaded. And then we can also here, for example, adapt the scalar range of the scale of the velocities, and we can also make this kind of section cuts. As you can see here, I can have a look at the font, of course, but when I want to get more insights, what's happening inside my tool, then I can just use the section here. I can cut it and then see what's happening. So this also takes a second. Now, we see what's happening inside here in the area where the two inflows, the melt of the two inflows are meeting, and we see we have quite some areas here where the melt velocity is lower. So this will probably lead also in less materials in the second layer here on the outside, and we use this information then to adapt the tool design. Okay, so that's it for the profile extrusion, but I would also like to give you more insights into the injection molding and what we're capable of doing in the injection molding. So it's basically the same when we want to upload the model. So we go to new 3D model and upload the part of the injection molding, as you can see at this part. And what we do is we click then here on new simulation, and we have to here do select more parameters. So in this case, we also say we want to do injection molding. We have to select the material for the injection molding. I will go with this one here. And as you can see here, different values for the mold temperature and the melt temperature, and then are then pre-selected. And we do this to give the user a first idea of what temperatures are reasonable for the mold temperature and the melt temperature, but you are also free to change this. So we can change the temperature here and also for the melt temperature. Then we have to define how the filling phase should take place. We can do this with a flow rate manually, but we can also define it by an injection time here in seconds. Or we can also say, okay, I don't have an idea for the filling time, for the injection time, please calculate it automatically within the software. And this is what will be then done by by the algorithms in the software. And this can be used, for example, if we're in a very early development stage and we don't know, we don't have enough information about the process, and we want to get some very first very good injection time, which can be calculated then here automatically. So I activated the button here to calculate the packing, the final cooling, and also the warpage. And I'll go here to next. And now we have to define where's our injection surface and where our injection points. So in this case, we have only one injection surface, which I just selected, but we can also create multiple injection points or surfaces. Like you can see here, I can define a diameter and just create it. And here you can see the different injection points we have. And yeah, we can manipulate it. So I can change the diameter, for example, here to 10. And I can also manipulate the coordinates. And then I can also remove them if I say, okay, I don't want them inside. And yeah, I can just delete them by this. So I accept this, we go to next. And now we have to define how the packing phase should take place. We can do this with the manual parameters also, which we enter. A packing pressure in bar or a packing time in seconds, or we can also do this automatically. Same for the cooling phase. So here we can enter either a time in seconds, or we can also let the software calculate this automatically. And we want to have a look at the warpage. So here we are getting, again, an overview about all the settings we've done in the simulation. And we can see is everything correct. And if that's the case, we can start the simulation. And then everything is completely automated again. So the simulation is submitted on the HPC cluster again, and the geometry preparation, the meshing, the simulation, also the post-processing, completely done automatically. And then we get a notification by email when the simulation is finished. So let me give you an idea of what the report looks like. So also this report is completely customizable up to your needs, and we can we get here an overview of the process data at first. So what are the process parameters that we've used in the for the starting of the simulation, but we'll also get information about the injection time, which was then calculated within the software, also the flow rates. We get information about the packing time, the packing pressure that is needed, and we get also information about the cycle time. So what are the cycle times of each stage, and also the total time, and what pressure is needed overall, and what are the clamping forces that are needed from a machine. So we have also these remarks and recommendations included. And this is something that is very new, and we get very good feedback from our customers for this. So what this basically is, we look at all the different measurements and all the different plots, and we have this kind of color scheme. So it's green, yellow, and red. So green means everything is fine. The filling quality in this case is good. There are no remarks. You can have a look at it, but you don't need to. Then we have the yellow color. So where we look at this injection pressure, for example, and in this case, it says we have a injection pressure between 1000 and 1400 bar, and this is a very high pressure, and this could lead to an issue. And you should probably have a closer look to it. And this makes it very easy for the user to look at the different measurements and say, okay, this looks fine. I will have a closer look to the injection pressure. And we're also having recommendations for the process, so how we can adapt the process. For example, we could increase the melt temperature or the mold temperature to reduce the flow resistance and then reduce the needed injection pressure. And we can also make changes to the geometry. For example, we can change the cross-section of the gate, and by this also reducing the flow resistance. So as you can see, we have this for all the different measurements. And here are also some wet in this case. So for example, the weld line angle. And yeah, it says that 20% of the weld lines are below a connection angle of 90 degrees. So this could be an issue because these weld lines have a weakened mechanical behavior, so they have a lesser strength. And we also have here process recommendations. So for example, to make changes to the temperature, maximize it, or also change the injection speed, or for the geometry also that we can think about the concept behind our arrangement of the gates to eliminate these weld lines, or also position them in an area that is not that critical. So overall, we are getting a very good idea of what's happening in my simulation and in which areas could be an issue and where should I have a closer look at. So let me give you an overview about the different measurements plot that we have included. So basically, here are all the important informations included. In this case here, the filling time, so for different filling levels, as you can see. So we get an idea of, do we have a uniform filling, do we have a short shot or not maybe, and how long does the filling take, so also from different views. And we get an information about the temperature, so how's the temperature distribution after the filling. Do I have maybe too high temperatures, which could lead to material damage and so on. We also have information about the melt front temperatures during the filling process. So which temperature does my melt front have at which positions in my part in the cavity. And then we can also detect areas where the melt front temperature is too low, which could lead then to further problems. So we have all these different plots, also like the plots here for the clamping forces for different directions. Depending on the parting line where I put it in the mold. And here you can see the plot for the weld line. So this could be a potential issue, as it was mentioned here in the recommendations. So what we see here is that, let me zoom in a little bit. So we have the weld lines that are visible, and we also see the angle at which these weld lines are formed when the melt fronts are connecting. So when the angle is too low, this could, as already mentioned, lead to a weakened strength of the weld lines. And we can also evaluate this in combination with the temperature of the weld lines. So we see here the temperature of the weld lines when they were formed. And we can evaluate this together with the information of the connection angle of the weld lines, and then make a better estimation about the strength of the weld lines. So we have this, the fill quality also included, as you can see here. So everything here is looking fine, and also the warpage included here. So we get an information about the final results that my part has. And the same here, if we want to have more information about what's happening, we can have a look here at the live viewer. So I can start the live viewer. You can see here the filling. I can also speed this up, as you can see here. So we have more or less uniform filling. We have complete filling. We can see the pressure distribution here in this case, but we can also look at different measurements like the temperature, as you can see here. So we can see the temperature distribution also during the filling, and then also here during the packing phase in this case here, and also here during the cooling. And we have all these different measurements, also like the warpage, where we can have a look at here at the part. And in the end, we can all use this information to make better decisions. So to see if we have a good part, if we can go to the production or not, or if we have to make modifications. And that's it from the product presentation. And for now, I will hand over to Hendrik again. Thank you.
Thank you very much, Simon. Impressive presentation. So we are a little bit over time, but I've seen in the F&A section, you have been quite busy and asked some questions. So at the end, we would like to, of course, answer those questions. Yeah, let's maybe start. Is the cloud secure? Typical question we often hear. The cloud basically is more secure than your private computer, I would say. Why is that? Because the cloud is managed by professionals, people who are experts in security and data protection. Everything you have on your private computer, if you have access to the internet, can be stolen much easier than it is the possibility in the cloud. Also, we have banking standard. In Germany, we have very high data protection rules we have to oblige, and we only calculate on German high-performance clusters. For example, the high-performance cluster Stuttgart, it's one of the fastest, or the fastest actually in Europe at the moment. It's certified by ISO 27001 and also TISAX. So the high-performance cluster we use in Stuttgart has the highest data protection certifications that are available on the market. So definitely, yes, the cloud is much, much more secure than your private computer where you use simulation software on premise. The next question, how accurate are the results? We are talking about simulations. Simon,
you can also answer if you want to.
I can answer it if you want. If you have anything to add, please add.
Okay.
Simulations are a theoretical approach. So simulations will probably never reach 100% accuracy, but we come close to that. The purpose of simulations is to see where are weaknesses in your design, where you should optimize your extrusion dies, where you should optimize your tools for plastic injection molding. So the purpose of simulation is to reduce the number of reworks you have to do. We have customers who say, I have to do 8 or 10 or 12 iteration loops because I do it by experience. And when they use simulation, they can reduce the number of iteration loops until 2, 3, or 4. So the purpose of simulation is not to be 100% correct. The purpose is to reduce and lower the number of development time, development costs, and iteration loops. Yes.
So yeah, maybe to add, so yeah, we also verify the results with our customers, and yeah, we always get the feedback that we have a very good match between the simulation and the reality. And if you go on our website, also you can find there the success stories from our customers that give you more information.
Yes, thank you, Simon. Then another question is, how much is one user license? So we don't have user license, actually. That's where we differ from other software programs. We have a contingent, I would say. So as many people as want from your company, from your organization, can have access to our software. It doesn't matter. It could be 1, it could be 10, it could be 100 or 500. We don't care. So you only pay per simulation. So for example, the lowest package we have is around 40 simulations for 10,000 euros. So it's like internet mobile connectivity on your smartphone. So you buy a package where you have internet access for 10 gigabytes, for example, and you use that. And it's the same for us. You buy a contingent of 40 simulations and you use that. That's pretty flexible and also fair, because let's say you buy 10 user licenses and 3 people leave your company, then 3 user licenses you pay, but you don't need at the end. Then one question, can I test it? I assume the person means, can I test the software? Yes, of course. You can test it before you sign any contract, before you buy anything, before you spend any money. Please test us. Contact us, or we contact you, because you signed up for this webinar. So we contact you after the webinar and give you the opportunity if you want to test us. You receive free access to our software for 1 month, and you receive a package of 10 simulations you can use and test. We just give you a very small onboarding because you don't need to be experts to operate our software, and then you are able to operate it by yourself and see what the results look like. And we also invite you after the testing to make a meeting with you and discuss the results. So you see, did it work for you? Is it a helpful tool you could use in the future? So before you buy anything, of course, I'm a normal person, I would test it too. So yes, that's possible. And one question, we are analyzing the flow behaviors of thermoplastics elastomer materials within extrusion molds. Could we conduct a single benchmarking exercise free of charge to compare your program to software we currently use? Yes, excellent question. Of course, yeah, we can do that. I will contact you after the meeting, and you have the possibility to test it, to do the benchmarking exercise, compare us to the solution you currently use, and then we speak, and then we have the results, and you have facts to decide whether you want to use us or not. So yeah, sure. So as far as I see, we are 11 minutes over the time. Thank you very much for your patience. Thank you, Can and Simon, for taking your time. It was a pleasure and a privilege to have you here today. These are, I would say, the final words of this webinar. We also put it on our website. We will contact you after the webinar to give you the opportunity to test us. And yeah, thank you. Have a great day and enjoy the summer. See you soon. Bye-bye.
Thanks. Bye-bye.
Have a good day. Bye-bye.